Now, welcome back to again the fifth session of the differential equation. In this session, I like to discuss with you the Bernoulli's differential equation. The general form of the Bernoulli's differential equation is y dash plus p of x into y is equal to g of x into y raised to n. Compared to previous one, this stage is the different type making the difference in this differential equation. For this to convert this is to be another linear form. We are firstly converting Bernoulli's differential equation into linear differential equation, then we will solve that linear differential equation. By solving that linear differential equation, we are finding a general solution for this Bernoulli's differential equation. For that equation 1 we divide with y raised to n. Therefore, it will become like y dash divided by y raised to n plus p of x into y divided by y raised to n is equal to g of x, and this we can rewrite as y raised to minus n into y dash is equal to plus p of x into y raised to 1 minus n is equal to g of x. By seeing this differential equation 2, it is easy to identify that this is not linear. We already told it is that we solved by 1 by changing 1 to be a linear differential equation. Now, 2 is also not a linear differential equation, that is why we have to make again 2 be a linear differential equation by a substitution. We substitute, put z equal to y raised to 1 minus m, that is the term of y with p of x. Now, differentiate both sides. While differentiating this on both sides, we will have z dash is equal to derivative of y raised to 1 minus n, that is equal to 1 minus n into y raised to 1 minus n minus 1 into derivative of y, that is y dash. That is z dash is equal to 1 minus n into y raised to plus 1 and minus 1 will go y raised to minus n into y dash. From here we can understand that this is y raised to minus n into y dash. The first term is y raised to minus n into y dash. The excess is 1 minus n only. We are taking that is to be here. Therefore, we will have z dash divided by 1 minus n is equal to y raised to minus n into y dash, and we have taken z is equal to y raised to 1 minus n, and as well as now we found y raised to minus n into y dash is equal to z dash divided by 1 minus n. So, put these two values to equation 2. By substituting that values to equation number 2, put these two values in equation 2. While substituting that is in 2, we will have y raised to minus n into y dash. We rewrite that as a z dash divided by 1 minus n and plus p of x into, instead of y raised to 1 minus n, we can rewrite this is y raised to 1 minus n as z, p of x into z, and as well as here is there is no change for the g of x, it will remains like that. So, I am taking this is to be here as well as to be here, make our differential equation is to be linear. Therefore, z dash is equal z dash plus 1 minus n into, we are taking 1 minus n to be here, 1 minus n into p of x into z is equal to 1 minus n into g of x. Now, see this differential equation. Compare this differential equation is our ordinary linear differential equation. See, instead of y dash, here we have a z dash is there, instead of p of x, here we have 1 minus n into p of x is there y only is here, and instead of g of x here we have 1 minus n into g of x is there. See, this equation number 3 is linear ODE. It is a first order linear ODE, and this is a first order linear ODE with a dependent variable as z. Instead of y, here we have dependent variable as z is here. While solving this linear differential equation, we can use either method. As we studied earlier, you can use the integrating factor method as well as method of variation parameter. In any of the method, you can solve this 3. You will get the value of z. That is the solution of equation 3. But actually, we need to find out the value of y. We have a relation is there. We substituted z as a y raised to 1 minus n. So, by that relation we can find out, while finding the value of z, from this relation we can find out the value of y. See, here we can solve this 3 is first time, and this is here p of x. Instead of p of x, here we have p of x, instead of p of x, here we have 1 minus n into p of x. Instead of g of x, here we have taking 1 minus n into g of x as g of x. So, while solving this, as I already told you, we can find z and we can find the value of y from this relation. Now, this is the method to how to solve Bernoulli's differential equation. See, we can move to the some examples. From that you can understand how can we solve very easily Bernoulli's differential equation by using the linear first order ODE. See, we can move to the first question. Example 1. Solve x into dy by dx, plus y is equal to xy cube, See, in our general form of Bernoulli's differential equation, we have general form of Bernoulli's differential equation. General form of Bernoulli's differential equation is y dash plus p of x into y is equal to g of x into y raised to n. So, this is not in this general form, the excess term is x. So, I am taking this as equation number 1. I divide 1 with x throughout. So, what will happen? This equation changes to dy by dx, plus this I am dividing with x, that is why 1 by x into y is equal to x by x will gone, now y cube only remains there. I am putting this as equation number 2. See, now our equation number 2 is of this form. Therefore, this is Bernoulli's differential equation. This is BDE. Is a BDE, Bernoulli's differential equation. See, dy by dx plus 1 by x into y is equal to y cube. Comparing this, you can find out this 1 by x as a function p of x. What about g of x? Y cube is there and g of x is not available here. Therefore, g of x is equal to 1. That is why this is a Bernoulli's differential equation by our method. What we did in our method, how to solve this Bernoulli's differential equation? We are dividing this differential equation throughout with this y cube. So, divide 2 with y cube. What will happen? This is equal to y raised to minus 3 in first part dy by dx plus 1 by x into y divided by y cube, that is y raised to minus 2 is equal to y cube divided by y cube is equal to 1. This is equation number 3. I am taking that as equation number 3, and we have to substitute for z. In our method, we substituted this 1 by x is the p of x. The term of y with p of x we are substituting for z. That is why we can substitute for z as z is equal to y raised to minus 2. Differentiate both sides. Differentiate. What will happen differentiating this one? This implies z dash, derivative of z we am treating as a z dash, that is dz by dx is equal to derivative of y raised to minus 2, minus 2 y raised to minus 2 minus 1, that is minus 3, into derivative of y, that is y dash. Now, take this minus 2 be here, therefore, this is implies minus z dash divided by, this implies minus z dash divided by 2 is equal to z y raised to minus 3 into y dash. See, to equation 3, this y raised to minus 3 into y dash minus y raised to minus 3 into dy by dx is we can replace by minus z dash by 2, and we are substituted y raised to minus 2 as z, therefore, this can be replaced by z. So, equation number 2 can be equation number 3 can be written as equation 3 becomes like this y raised to minus 3 into dy by dx we replaced by minus z dash divided by 2, as well as this is the plus 1 by x y raised to minus 2 we replace by z, and the remaining the right side is 1, it will remain like that. And I have to make this as a linear, instead of here z dash is there, minus 1 by 2 is there, I like to remove this minus 1 by 2 to this part. Therefore, this can be changed as z dash minus 2 divided by x z is equal to, I am taking this minus 1 by 2 to here and here, therefore, one more minus 2 be here. Now, what we got, it is a differential equation, that is not only a differential equation, it is a first order linear ODE. First order linear ODE. Now, our BDE we converted into this first order linear ODE. Now, we have here this is minus 2 by x, we can treat this minus 2 by x as p of x, and this minus 2 we can treat as g of x. To solve this first order linear ODE, I am using the integrating factor method. How can we find the integrating factor? We have the formula for finding the integrating factor. This is equal to e raised to integral of p of x dx. E raised to integral of p of x dx. What about p of x? P of x is the minus 2 by x. Therefore, this is equal to e raised to integral of minus 2 by x dx. That is equal to e raised to minus 2 log x is equal to e raised to log x raised to minus 2 is equal to x raised to minus 2. Now, x raised to minus 2 is the integrating factor, that is integrating factor is equal to 1 by x square, x raised to minus 2 is 1 by x square. That is why we are able to find out solution for our differential equation 4, which is linear ODE in equation 4 I am treating as this, which is linear ODE in z. We can find out the value of z of x. So, the solution is general solution of 4 can find. How can we find the general solution of 4? We have the formula, instead of y into integrating factor, as we discussed earlier, instead of y here we are discussing z into integrating factor is equal to integral of integrating factor into g of x is there, but is actually here g of x is minus 2 dx plus c. Now, z into integrating factor is 1 by x square is equal to integral of 1 by x square into minus 2 dx plus c, minus 2 dx plus c. So, z by x square is equal to minus integral of 2 dx by x square, minus 2 dx by x square plus c. See what will happen, z divided by x square is equal to minus 2 x raised to minus 2 plus 1 divided by minus 2 plus 1 plus c. 1 by x square, we can treat 1 by x square as a x square x raised to minus 2, derivative of x raised to n is equal to x raised to, sorry, integral of x raised to n is equal to x raised to n plus 1 divided by n plus 1. Therefore, this is equal to z divided by x square is equal to minus 2 x raised to minus 1 divided by minus 1 plus c. Therefore, z divided by x square is equal to 2 by x plus c. Therefore, we can take this x square to here and here. Therefore, z is equal to x square by x, that is 2 x c into x square plus c x square. This is z is equal to 2 x plus c x square is the general solution of equation number 4, is general solution of equation number 4. It is the general solution of equation 4. Now, see, actually we need to find the general solution of the BDE, Bernoulli's differential equation, which is equation number 1, but we found z is equal to 2 x plus c x square. From here we substituted, it is that we have z is equal to y raised to minus 2. We have z is equal to y raised to minus 2. So, we replace y raised to minus 2 be here. Therefore, this equation number 5 becomes how can we rewrite this equation number 5? Instead of z, we just replace y raised to minus 2, that is y raised to minus 2 is equal to 2 x plus c x square. That is y raised to minus 2, we can treat this as 1 by y square. This is equal to 2 x plus c x square. I am taking this y square to be here. Therefore, we can replace this as 1 is equal to 2 plus c x into, I am taking 1 x is out, x y square. That is, this is the general solution, y square into x into 2 plus c x is equal to 1. This is the general solution of 1. Here we, instead of y, most of the differential equation we generated the solution as y is equal to. In this Bernoulli's differential equation, we write this as a mixed type, that is y square into x is equal to this one 2 plus c x is equal to 1, which both x and y are mingled, and this type of solution are only exists for only our Bernoulli's differential equation. In some cases, we are existing the solution like linear differential equation. See, one thing is that for solving BDE, Bernoulli's differential equation, we are taking the methods of the linear differential equation, first order ordinary linear differential equation. We can move to the next example, example 2. Example 2 dy by dx plus x sin 2y sin 2y is equal to x cube cos square y, x cube cos square y. See, I am taking this question as equation number 1. Our aim is to solve this differential equation 1, and one thing is that my question towards you is that this is a BDE, is this is a BDE, is this is a Bernoulli's differential equation. It's as we mentioned in general form of the Bernoulli's differential equation, we are unable to see this as a BDE. But even though with the function of x here in the right side, there is a function in y is there, cos square y is there. So, we are trying to solve this as a, we are interested to treat this equation also as a BDE. As how we solve BDE, we will solve this differential equation. So, we are, as we done in BDE, here the function term involving y is cos square y. That is why we are dividing throughout, with a cos square y. So, 1 is divided by cos square y. So, equation 1 becomes 1 divided by cos square y dy by dx plus x into sin 2y divided by cos square y is equal to x cube. See, instead of 1 by cos square y, I like to rewrite this as a 1 by cos square y as a sec square y. We have a trigonometric formula is there, and into dy by dx plus x into sin 2y. We have sin 2y is a 2. We have trigonometric formula 2 sin y cos y divided by cos square y. Yeah, it will keep there as like that, x cube is there. And see here we have 1 cos y is here, and we can remove 1 cos y from the denominator. So, we can change the differential equation is again sec square y dy by dx 2 into x plus 2x into, here remains only sin y divided by cos y, that is tan y. Sin y by cos y is there, that is tan y. This is equal to x cube. Now, see, this is again came to the second type of differential equation. Now, we have to make this equation 2 as a linear differential equation. To make this is a linear differential equation, we substituted z as the function in y, the term in y which is coming with the p of x. Here 2x is the px, here 2x is the px. So, that we are substituting put z is equal to the function in y or the term in y coming with the p of x is tan y. We substituted tan y as the z. Now, next step is, as we did in former problem, differentiate. While differentiating this one, we will have z dash is equal to derivative of tan y. Derivative of tan y is sec square y, and because of this is a function in y, we have to differentiate. Again we have y dash is there, dy by dx is there, sec square y into y dash. See, here the first term is sec square y into y, and the tan y is z. We can put in equation 2. Therefore, equation 2 becomes, how can we change the equation 2? See, our equation 2 is sec square y into dy by dx. We found that sec square y into dy by dx, sec square y into y dash is equal to z dash. Therefore, instead of that we can replace it by z dash, and z dash is there, and plus 2x into px is there, 2x into, instead of tan y we substituted tan y as a z. So, we write this as z is equal to x cube. Now, I am taking this is as a equation 3. Compare this equation 3 with our ordinary linear differential equation. Our ordinary linear differential equation, we know this is equal to y dash plus p of x into y is equal to g of x. The same format keeps this function. Instead of y, here there exists only z is there. Now, the differential equation 3 is a linear first order ODE. Now, this is a linear first order ODE with p of x as 2x, with p of x as 2x and g of x as x cube and g of x as x cube. That is why we can find out. I am using the integrating factor method here. So, we have to find integrating factor. To find integrating factor, how we will find the integrating factor? Integrating factor is equal to e raised to integral of p of x dx. Here we have p of x is equal to 2x. Therefore, this is equal to e raised to integral of, instead of p of x we replace it by 2x, the function 2x is there. So, we will have e raised to integral 2x dx is there. Therefore, this is equal to e raised to integral 2x is there, 2x square by 2. We can cancel 2 and 2 and we will have e raised to x square. This is the integrating factor. The integrating factor is equal to e raised to x square is there. We have the formula, general formula to find general solution for whom? For 3, which is the linear differential equation, general solution for 3. And general solution for 3 we have, instead of y here we have z into integrating factor is equal to integral of integrating factor into g of x dx plus c. See, we found the integrating factor is here and as well as we have g of x is here. This is g of x, x cube is the g of x. So, we have z into integrating factor is e raised to x square is equal to integral of integrating factor, again we are putting e raised to x square is here. What about g of x? G of x is the x cube dx plus c, x cube dx plus c. See, while solving this one, we will get the general solution for 3. Keep in your mind, we substituted z is equal to tan y. Keep in your mind, we substituted z is equal to tan y. At last, we have to use this value, and this is we have this is equal to z e raised to x square is equal to e raised to x square into x cube dx plus g. So, z e raised to x square is equal to, I am just constructing this as a integral of e raised to x square into x cube. I am writing x cube as x square dx plus c. Make this as 2. I am writing 2 is here. To compensate that 2, I am dividing by 2 here. So, this is for I can substitute, instead of put u is equal to 2x, sorry, put u is equal to x square, put u is equal to x square. So, du is equal to 2x dx, du is equal to 2x dx. So, we can substitute these values to be here. Therefore, this equation is z e raised to x square is equal to 1 by 2 into integral of e raised to x square is u, e raised to u, 2x dx is du, x square is u, e raised to u du plus c. See, we can rewrite this as 1 by 2 into integral of, I am treating u as a first function and this e raised to u as a second function. By integration formula, we can rewrite this as first function u into derivative of e raised to u minus integral of derivative of u is 1 into e raised to u du. Therefore, this is equal to 1 by 2 into u e raised to u minus integral of e raised to u is again e raised to u plus c is here, just I forgot that c is here also. So, again we are coming to the conclusion of the problem. This is our integrating factor is z e raised to x square is there 1 by 2 into, we can replace u by x square, we can replace u by x square e raised to x square minus e raised to x square plus c. Say z e raised to x square is equal to 1 by 2 into e raised to x square into x square minus 1 plus c. See, I am dividing e raised to x square to here and here. So, what will happen? Z is equal to 1 by 2 into e raised to x square by e raised to x square will go on x square minus 1 plus c divided by e raised to x square, it will comes to numerator plus c e raised to minus x square. This is the general solution of the ordinary linear differential equation, that is equation 3. Now, we just replace z by tan y, this is our substitution, replace z by tan y, So, what will happen? It is that tan y is equal to 1 by 2 into x square minus 1 plus c e raised to minus x square. This is a general solution for 1. This is a general solution for ordinary differential equation 1, that is our BDE. Not a BDE as like a BDE, but even though we are treating that like a, that is a BDE, even though we are treating that is a BDE, Bernoulli's differential equation. Bernoulli's differential equation is a nice part of the differential equation. If you are going through more and more problems on it, you can enjoy this differential equation. We will come on the next session with new type of method of differential equation. Okay, thank you very much.